Yes, please start.
Okay, thank you. I'd like to thank the organizers to have a talk in this nice conference. Okay, the notion of a virtual knot was introduced by Professor Kaufman. In this talk, we introduce several polynomial invariants of a long virtual knot and give two applications concerning connected sums of a pair of virtual knots and the supporting genus of a long virtual knot. Throughout this talk, we always assume that every long virtual knot is oriented. We will start the definition of the polynomial invariants of a long virtual knot first. Okay. Let D be a diagram of a long virtual knot K, and C1 to Cn the classical crossings of D. To define the polynomial invariants, we prepare two notions as follows. The first one is the type of a crossing, of a classical crossing. When we walk along the diagram D with respect to the orientation, if we go over Ci first and then under Ci second, then the crossing Ci is of type 0. On the other hand, if we go under Ci first and then over Ci next, second, then Ci is called of type 1. We denote by IA the set of indices of the classical crossings of type A for A is equal to 0 or 1. Okay. This. For example, we consider this diagram of a long virtual knot, which has 5 classical crossings, C1 to C5. As the crossing C1, we go under C1 first, and then over Ci second. So the type of C1 is 1. By checking the types of all the crossings, we see that the crossings of type 0 are C2 and C4, and the crossings of type 1 are 1, 2, 3, like this. Okay. Next, we smooth the diagram as the crossing Ci coherently. Then we obtain a pair of curves consisting of a loop component alpha I and arc component beta I. Okay. Now we consider a surface realization of the diagram D. Here, a surface realization is a diagram with no virtual crossings on some oriented closed surface equipped with a base point at infinity by identifying the endpoints of the long virtual knot here and here. Under this identification, we will regard the curves alpha I and beta I as the first homologic classes of the surface, of this surface. Okay. Then we can define a Laurent polynomial WA by this equation for each A. Roughly speaking, this polynomial is a formal sum of the intersection numbers of alpha I and beta I as homologic classes and equipped with the sign of the crossing for all the crossings Ci of type A only. Then we see that these two polynomials, W0 and W1, are invariants of a long virtual knot K, and call them the 0 and 1 rise polynomials of K, respectively. Okay. Furthermore, we can define 12 Laurent polynomials, FAB, GAB, HAB, by these equations for each A and B. For any types A and B, the polynomial FAB is a formal sum of the intersection numbers between alpha I and alpha j, equipped with the product of the signs of the crossings here. For all the pair of crossings, Ci and Cj of type A and B, respectively. Then we see that this polynomial FAB is an invariant of a long virtual knot K. Similarly to FAB, we can consider the intersection number between alpha I and beta j. Because that alpha I is the loop component, beta j is an arc component, which are obtained from the diagram by smoothing at the crossing Ci. When we consider this sum, then the sum is invariant under Reidemeister moves 2 and 3, but not invariant under Reidemeister move 1. So by adding the correction term here, we obtain, we see that GAB is also invariant of a long virtual knot K. Here, WB is the omega B is the rise of type B, which is the sum of the signs of crossings of type B only. WA is the rise polynomial, A rise polynomial, defined as above. The polynomial HAB is similarly defined by using the intersection number between beta I and beta j with some correction terms here. Okay. So anyway, these 12 polynomials, FAB, GAB, and HAB are all invariants of long virtual knot K and called the intersection polynomials. Okay. We give an example here. These three long virtual knots K1, K2, and K3 are obtained from a trefoil knot by replacing a middle, right, or left crossing with virtual 1, respectively. Then the rise and the intersection polynomials of these long virtual knots are given as shown in this figure, in this table. We remark that the intersection polynomial F10 is obtained from F01 by replacing T with T inverse. Similarly, H10 is obtained from H01 by replacing T with T inverse. So we omit these polynomials from the table. Anyway, in this example, these three virtual knots are all distinct by W0 zero rise polynomial only here. But of course, this is not a general case. We remark that if 0, of K1 is non-zero, but if AB vanishes for K2 and K3 for any AB, this phenomenon is very important in our study, which will be explained later. Also, anyway, we can also detect the difference under symmetry, such as orientation reverse or mirror reflection. And we also give the complete table of long virtual knots up to 3 classical crossings. There are 37 long virtual knots with at most 3 crossings up to symmetry, but we omit them in this talk. Okay. Now, we will give 2 applications of these polynomial invariants. First, we consider the closure of a long virtual knot. Okay. It is obtained, the closure is obtained by closing the long virtual knot and forgetting the base point of infinity. We denote by CLK or K hat the closure of a long virtual knot K. Although this closing map is surjective, it is not injective. In fact, the 3 long virtual knots K1, 2, 3 in the previous example give the same closure, which is called the virtual trefoil knot. On the other hand, we have already seen that these 3 long virtual knots are all different. So this map is not injective. Therefore, it is natural to consider the preimage of a virtual knot by this closing map. Then we have the following. For any virtual knot K, there are infinitely many long virtual knots whose closure is given knot K. In other words, the preimage of any virtual knot by this closing map is infinite. Okay, this theorem is obtained from the following lemma immediately. For any virtual knot K and any Laurent polynomial Ft with F1 is equal to 0, then there is a long virtual knot K such that the closure is K, the given virtual knot K, small letter K, and the Rise polynomial, zero Rise polynomial W0 is Ft. Okay, we can choose the Laurent polynomial Ft arbitrarily under the condition F1 is equal to 0. So we can construct infinitely many long virtual knots K whose closure is the given virtual knot. Okay. By using the invariants of a long virtual knot, we can construct the invariants of a virtual knot as follows. For a virtual knot K, we first take a long virtual knot whose closure is K. Then the polynomial W is obtained from the sum of W0 and W1 T inverse of the long virtual knot. we can prove that this does not depend on the particular choice of a long virtual knot whose closure is K, so that W is an invariant of a virtual knot K. This polynomial W is called the rise polynomial of a virtual knot, which is equivalent to the affine index polynomial introduced by Professor Kaufman. Also, the polynomials 1 or polynomials 2 are obtained from the intersection polynomials of the long virtual knot as this equation. For example, the first polynomial is F00, G00, G11 with T inverse, H01 T inverse. Then we obtain an invariant of a virtual knot. These are, in this talk, we omit the definition of the third polynomial. Anyway, these are called the first, second, and third intersection polynomials of a virtual knot K, respectively. Okay. It is known that, unlike the classical case, the connected sum of a pair of virtual knots is not determined uniquely. To give a precise definition of a connected sum of virtual knots K and K prime, we first take long virtual knots whose closures are K and K prime, and then take the closure of the sum of these long virtual knots, like this. Okay, we denote by CKK prime, the set of connected sums of K and K prime, by this definition. Then we see that this set is infinite for any pair of virtual knots. This one. This theorem is obtained from the connected sum formula of the first intersection polynomial by this lemma. Okay, by this equation. By this equation. This formula says that the first intersection polynomial is not additive under a connected sum generally, but the difference is described by using the 0 and 1 rise polynomials of the long virtual knots. As mentioned above, since the 0 rise polynomial can be chosen arbitrarily, we can prove this theorem with some argument. We can prove this theorem by using this lemma. We remark that the other intersection polynomials of a virtual knot, such as the second intersection polynomials, are also not additive generally. But we omit the connected sum formula here. Okay. This is the first application of polynomial invariance. Another application of the polynomial invariance is about the supporting genus of a long virtual knot. Let sigma GM be the oriented compact surface of genus G with M boundary circles. For a virtual knot diagram D, we can consider two kinds of surface realizations with boundary as follows. The first realization is on some surface with one boundary circle, such that both endpoints of the diagram lies on the boundary. This is essentially the same as the previous realization with a base point at infinity, okay, by shrinking this circle with one point. On the other hand, the second realization is on some surface with two boundary circles, such that the endpoints of the diagram lie on different boundary circles. Okay. For a long virtual node K, the one supporting genus of K is defined to be the minimal genus of all surface realizations with one boundary circle, denoted by SG1K. Similarly, the two supporting genus of long virtual knot is defined to be the minimal genus of all surface realizations with two boundary circles, denoted by SG2K. Okay, then it follows by definition that we have these inequalities easily. Okay, in fact, if a diagram lies on sigma G1, then it can lie on sigma G2 by dividing this circle into two circles, like this. Also, if a diagram lies on sigma G2 with two circles, then it lies on sigma G plus 1, 1, which induces this light inequality here. Okay. This lemma implies that the first, the one supporting genus is equal to two supporting genus or two supporting genus plus 1. So we see that, then we see that this one. Then we see that there are infinitely many long virtual nodes K such that which realize these inequalities. The first assertion is the first supporting genus is equal to the second supporting genus plus 1. The second assertion is there are infinitely many virtual node K which realize this equality here. But we remark that if K is a long classical node, then the one supporting genus and two supporting genus are equal to 0 both. So we give a condition, additional condition here. Anyway, to prove the first assertion, this one, we consider this long virtual node Kn. It is obtained from a 2n plus 1 torus knot by replacing the most right crossing with a virtual one here. Then we see that the zero polynomial W0 of this long virtual node Kn is equal to n times t minus 1. Since this zero polynomial is non-zero, which means that it means that Kn is non-classical, so that the one supporting genus is greater than or equal to 1. Of course. On the other hand, Kn has a surface realization on the annulus, as shown in this figure. This implies that the two supporting genus of Kn is equal to 0, because the genus of annulus is equal to 0. Okay. Therefore, we see that the one supporting genus is equal to 1 and two supporting genus is equal to 0. Okay. To prove to give the proof of the second assertion, we prepare one lemma as follows. If a long virtual knot, if the two supporting genus of long virtual knot Kn is equal to 0, then the intersection polynomial FAB is always equal to 0 for any AB. In fact, since the two supporting genus is equal to 0, it has a surface realization on an annulus. Okay. At any crossing CI, we consider the loop, which is obtained from the diagram by smoothing the crossing CI. Then, as a homology class, alpha I is presented by integral times of the meridian only. Okay. This is some example. Alpha I is always a meridian. Some meridians like this. Therefore, the intersection number between alpha I and alpha j is equal to 0. Which means that the intersection polynomial FAB is equal to 0 for any AB. By using this lemma, we can prove the second assertion of the theorem as follows. We consider this long virtual knot. This is obtained from 2n plus 1 torus knot by replacing the second crossing from the right with a virtual one. Then Kn has a surface realization on the one punctured torus as shown in this figure. So that the one supporting genus of Kn is at most 1. Okay. On the other hand, we see that the intersection polynomial F00 is equal to nt minus 2n plus nt inverse. Since this polynomial F00 doesn't vanish, the two supporting genus is non-zero by the lemma. So the one supporting genus and two supporting genus of this virtual knot Kn is equal to 1 both. Okay. Finally, we consider filtration. Yes. This is the last page. The supporting genus of a long virtual knot induces a filtration of long virtual knots as follows. Let LVG1 denotes the set of long virtual knots whose one supporting genus is at most G. LVG2 is the set of long virtual knots whose two supporting genus is at most G. Then, by the previous lemma, we have already seen that LVG1 is a subset of LVG2, and LVG2 is a subset of LVG plus 1, 1. So we have this filtration, like this. Okay. In our study, although we don't have any idea to prove a difference between any two adjacent subsets in the sequence generally, but we see that there are strict differences between first four subsets, here, here, and here. that is, LV01 is a proper subset of LV02, and it is also a proper subset of LV11, and it is also a proper subset of LV12. Here, here, and here. Okay. But the first two inequalities has already proved. This one and this one has already proved in the previous theorem. So it is sufficient to prove this part. To prove that LV11 is a proper subset of LV12, we give a necessary condition of a long virtual knot belonging to LV11 here. Okay. Then, to prove this this part, we prepare one lemma here. This is not easy, but anyway, if a long virtual knot lies in LV11, then the sum of four intersection polynomials F01, G00, G11 with T inverse, H01T with T inverse is reciprocal. For example, since this long virtual knot, this long virtual knot is not in LVV. This long virtual knot does not satisfy this condition in this lemma. In fact, the sum of the polynomials is equal to this one, which is not reciprocal. So that this long virtual knot is not in LVV, but in LV12. So we have this inequality. LV11 is a proper subset of LV12. Okay. That's all. Thank you very much.